assignment 1, remark 1. If f is real and bounded function on closed interval ab and alpha is monotonically increasing on closed interval ab, then prove that LPF alpha is less than equal to UPF alpha. This is a very easy proof, right? So let's start. Let me take a partition P that is x0, x1, x2 up to xn. This will be any partition of closed interval AB. And let's define capital Mi to be the supremum of fx over the segment xi minus 1 and xi, and small mi to be the infimum of fx over this closed interval xi minus 1 xi. So from here we get then small mi is less than equal to capital Mi. Very fine. For all I is equal to 1, 2 up to n. Right. In the next step, I'm going to multiply delta alpha I on both the sides. We just have to remember the definition of UPF alpha and LPF alpha. And the definition for LPF alpha is what? It is a summation of all small mi into delta alpha I. Similarly, UPF alpha is the summation of all sums capital Mi into delta alpha I. So that's why I'm going to multiply delta alpha I on both the sides. So it is Mi delta alpha I less than equal to capital Mi into delta alpha I. Again, I have to write for all I is equal to 1, 2 up to n as why there is less than equal to sign, because I know that delta alpha I is greater than equal to 0, right? Okay, now the next step, just take the summation on both the sides now to complete the definitions for LPF alpha and UPF alpha. So this implies I'm taking this summation, I going from 1 to n, Mi delta alpha I less than equal to summation I going from 1 to n, capital Mi delta alpha I. And this is nothing but your LPF alpha and this is less than equal to UPF alpha. Hence proved. Take this remark just as a note to you. Then is the remark 2. If f is real and bounded functions on closed interval AB and alpha is monotonically increasing on closed interval AB such that small m is given to be the infimum of fx over closed interval AB and capital M is the supremum of fx over closed interval AB, right? And if we thought about small mi, then this will be your infimum of fx over interval xi minus 1 xi, right? So in this case, if mi is the infimum of fx over this interval, which is a closed interval, from this bigger interval, closed interval AB, right? Then small mi is always greater than equal to this small m, right? So infimum of fx over bigger interval is always less than equal to infimum of fx over smaller interval, right? Just keep this in mind. So here it is given that small m is the infimum of fx over closed interval AB and capital M is the supremum of fx over closed interval AB. Then I have to prove that small m into alpha b minus alpha a is less than equal to LP of alpha less than equal to UP of alpha less than equal to capital M alpha b minus alpha a. This is nothing but your summation of delta alpha i's, right? Okay. So it is very easier to prove that LP of alpha is less than equal to UP of alpha. We just take the help of the proof just we have done before this remark, and just we have to apply the definitions. It's also a very simple proof, right? Okay. Again, I'm having my partition P is equal to x0, x1, x2 up to xn, be any partition of closed interval AB. And then I have to again define capital Mi to be the supremum of fx over this closed interval xi minus 1 xi, and small mi is the infimum of fx over closed interval xi minus 1 xi. Then from here we can say that this small mi is less than equal to capital Mi. Very fine. But because it is given that small m is the infimum of fx over the bigger interval AB, right? So that small m, because it is the infimum of fx over closed interval AB, this is always less than equal to this mi, which is the infimum of fx over that small closed interval, that segment xi minus 1 xi, right? So it is always greater than that infimum of fx over bigger closed interval. Similarly, here if I am having capital Mi, which is the supremum of fx over this small segment, this is further less than equal to capital M, which is the supremum of fx over bigger closed interval AB. Is it fine, clear? Just learn this or remember this for all I going from 1, 2 up to n. Alright. Now because I need alpha b minus alpha a, so I just multiply all over with delta alpha I, right? So this is m delta alpha I less than equal to mi delta alpha I less than equal to capital Mi delta alpha I less than equal to capital M delta alpha I. For all I is equal to 1, 2 up to n. Right. This implies in the next step, what should we do? Take the summation all over again, like in the previous proof. So summation going from 1 to n delta alpha I less than equal to summation I going from 1 to n small mi delta alpha I less than equal to summation I going from 1 to n capital Mi delta alpha I less than equal to m. It is nothing to do with the summation. There is no I defined. So summation, it is taken outside. It is delta alpha I. Alright, so this is equal to m. Now sum of all delta alpha i's is alpha b minus alpha a. In between all those cancelled out. So it is complete sum is alpha at b minus value of alpha at a less than equal to, this is nothing but your LPF alpha less than equal to, this is a definition for UPF alpha less than equal to m. This is also the complete sum, that is alpha at b minus alpha at a. In between terms all cancelled out. Hence proved. Thank you so much. Have a very nice and good day.